welcome back. Just let me check once if the stream is working, then I can start my class. Just give me a second. Yeah, so it is working, so I can start my class. Hi Rakesh. Yeah, so it is working, so I can yeah. Hi Rakesh. So if you are following our channel, you should know that we have started electrostatic potential and capacitance, but I had to stop the class in the middle of it because there was some power failure. So that's why I have decided I will go through the initial part, whatever was covered in our previous lecture that was cut short. I will revise that once and then I will go into the next topics. Right, so basically it is a continuation of the previous lecture. So if you see in our previous part, we have discussed the chapters of summary, basically electric potential, potential energy and potential. So relationship between potential energy and potential, they are not same, by the way. Electric potential due to a point charge, system of charges, potential as well as potential energy, equipotential surface, relationship between electric field and potential, potential energy due to system of charge, and potential energy due to dipole. So these are our topic of the discussion today. In other parts, part 2 and part 3, sorry, this part already discussed. I am really sorry. This part was discussed in our part 1. This one already covered in our part 1. Okay, this is part 2. Sorry. Part 1, this part is already covered. This is part 2. So part 2 we are going to cover this portion. Okay, this portion we are going to cover relationship between so what are conductors, dielectrics, some properties of conductors, some properties of dielectrics, and polarization. These are the topics that we are going to discuss in today's session. And in the third part, this part will be covered in our part 3. What we will cover: capacitor, the parallel plate capacitor, combination of capacitor, energy stored in a capacitor. Right, so these are the things that we are going to cover in our part 3. So this is the chapter summary. Now let's move on with the discussion. So electrostatics of conductors. Metallic conductors contain mobile charge carriers, namely electrons. In a metal, the outer or valence electrons part away from the atoms and are free to move. These electrons are free within the metal but are not free to leave the metal. So I gave you one example that your parents have locked you inside your room. So basically you can move within your house, but you are not allowed to go outside the house. So electrons are like that. So they are someone naughty children, they are not studying, so their parents, the metal, they locked them inside. So they said that okay, whatever you want to do inside the metal, do not go outside the metal. You can move around the in the room, and they are being naughty child, so they are moving around the room randomly. Okay, so they are in constant motion, but as I mentioned, without any external help, they will not be able to move out of the metal. Okay, the free electrons form a kind of gas. They collide with each other and with the ions move randomly in different directions. In an external electric field, they drift again in the direction of the field. So external field, in the absence of external electric field, they basically are like the ideal gas. You have studied ideal gas. There the gas particles are moving in random motion, so, and not only they are moving in random motion, they are colliding with each other. So they are actually moving like a gas. Okay, similar to that of a gas, the electrons are basically moving in random direction. They do not have any particular direction. They are moving in the random motion. Okay, now electric field, you can consider this to be like a classroom. Now you are inside a classroom, the students are disturbing, like it happens to every one of you. So you went to your college, everyone is discussing, everyone is chatting, but as soon as the teacher entered, you all got silent, you tried to focus in the teacher, but in between you are still chatting between yourselves, right? So the some randomness is still there, but because the teacher is there, you have to focus in the class, and that's why the electrons are also in the presence of external electric field. Even though they are moving in the random direction, as soon as you apply the electric field, the electrons start to drift. Drift means their motion is now slowly aligned in the particular direction. Even though they are not actually following the straight path, they can go slight curved, but overall motion is now fixed in a particular direction. So this overall motion is called drift. If you consider the overall motion in the past, overall motion was 0. Okay, overall motion was 0, because even though they are moving randomly, if you add a random motion, if you take the sum of random motion, it always comes out to be 0, right? Because if you can go positive, you can come back negative. So after some time, some point of time, if you add all the motion, basically it gives you a 0 motion. But when there is an electric field, the electrons are on an average moving in a particular direction. That is called drifting or drift motion. Okay, more about the drifting we will discuss in our next chapter, current electricity. There we will start with the drifting of electron in the presence of external electric field. Microsoft account. Sir, I joined an offline KCET batch for discipline, and they are doing those fat MTG objective KCET books which contain topic wise 150 plus questions per chapter of my patterns. Is really that many important? Should I switch Pariksha Veera drops for question practice? MTG is enough for rank 1000 in KCET. See, MTG do have some good questions, but trust me when I say that 50 to 60% of those questions are actually not that relevant for KCET. 50% questions are good, but another 50% questions are not good. Okay, they have the questions, even though the questions are very good to solve. For example, as a teacher, I like those questions. I enjoy solving those questions, but if in terms of exam importance, not all questions are important. Especially for physics, I can say that mathematics may be different, chemistry may be different. For physics, what my experience from KCET and from whatever is given in MTG, for question practice, 50% questions are good, 50% questions are not good. Okay, you can still decide on Pariksha Veera. Pariksha Veera is starting from 6th of July. And if I remember, you are dropping, right? Microsoft account, you have dropped this year, right? So you can pay only 3,500 rupees for one whole year course. So you can join us. Okay, we will discuss in detail. We will also solve questions in the series as well. Okay, so don't worry about that. Question practice will be happening constantly, right? So obviously, as a teacher, I will tell you to join Pariksha Veera, but you have to take the step because you have already joined an offline course, offline batch. Check there few weeks more. Okay, if they are doing anything better, if they are giving you enough materials for study, then you can keep with that. But if you are someone who can study from online, then definitely Pariksha Veera will be a game changer for you as well. That is my guarantee. At least for physics, I will be teaching, and I will teach as depth as possible, and we will practice a lot of question. And also in YouTube also we are doing a lot of question practice. We did a quiz on Friday. Not many students were there, unfortunately, but we did a quiz in our live class as well, right? So from where to solve questions? Good question. What I find that first of all, PYQs. PYQs are the best book for practicing question. Secondly, for example, the questions that we give you here are mainly from the question bank prepared by our own in-house team. They have a very good question bank. So from there you can practice, but obviously that is not accessible to everyone. in there. But yes, so in future we will be having Abhyas test series as well. So Abhyas test series is something which is very good in terms of question level and question preparation. It was praised by toppers. Every year we produce toppers by from the Abhyas test series itself, which is only a test series, which is not included with any course or anything, but only a test series. So if you can purchase that later on, that will be also very beneficial, because Abhyas test series is basically curated for KCET level question practice only. It is not from some higher level question, because what I feel that MTG textbook, obviously 50% as I mentioned are good question, 50% questions are slightly higher than KCET level. Okay, so that is one issue. PYQs you cannot skip, PYQs you have to practice, PYQs you cannot skip at all. Now electrostatics of conductor. So what is electrostatics of conductor? So if you go back in the past, okay, so if you apply an external electric field, what happens inside the conductor? That is very important point to understand. Okay, inside a conductor, electrostatic field is always 0. At the surface of the charged conductor, electrostatic field must be normal to the surface at every point. So these are the 2 points mentioned. But why electrostatic field inside a conductor is 0? So if you consider a conductor is basically consisting of an atom which has a positive charge and some electrons are orbiting around the nucleus, right? So that is the structure of the atom. Now what happens is that the electrons, some of the electrons are already free. So this is the basically ionic atom left, right? Outermost electrons are free to move inside the conductor. Innermost electrons are still bound to the nucleus, so they are not able to move. So this basically can be considered as positively charged ion. So let me write it like that. So positively charged ions and electrons. So these are the 2 main ingredients inside the conductor. Now what happens, the ions generally stay not move, they are basically not active. Electrons are active enough, they are moving around, right? Now if you apply external electric field, something happens. That what happens is that electric field, in the presence of electric field, positive charges move in the direction of electric field, negative charges move in the opposite direction of the electric field. So after some time, all the positive ions accumulate on the side which is the direction of electric field, and all the electrons accumulate in the opposite direction of the electric field. Now they also develop a internal electric field of their own, because electric field is from positive charge to negative charge. So there is a internal electric field developed inside the conductor. So this internal electric field cancels the external electric field. So the external electric field and the internal electric field, they are exactly equal and opposite in both sides. So that means they cancel each other, and because of the cancellation, the net electric field inside should be always 0. So electric field inside a conductor is always 0. We have seen that in case of a electric shell where we have charged it, even if it is charged shell, the electric field was 0 inside, and if it is not charged also, the electric field is always 0 inside a conductor. Okay, no matter what, electric field is always 0 inside a conductor. Okay, so that is one very important point to remember. Okay, if you have a conductor, you apply external electric field inside will be 0. Now next, the interior of conductor can have no excess charge in the static situation. Any excess charge must reside on the surface. So excess charge means what? So suppose you have either you have removed some electron or you have added some electron. So that is basically excess charge. By default, metal has equal number of charges. So that is one positive ion and one negative electron. So together the total charge was 0. Together the total charge was 0. Now if you can somehow remove some electrons, okay, from the metal, then the metal will become positive, because now the balance is gone. You can remove electron or add electron, there is a process for that. So if you can add electron or remove electron, then the metal will become charged. Now this charge will not stay inside the metal. It is like a floating ball, plastic ball. Okay. Where should I do topic wise questions from? So topic wise question for KCET, there are only 2 books, MTG, and I think another book was there, I forgot the publication. So you can practice from there. Okay, topic wise question, but as you know that not all topics are important for KCET. You have to choose the topics which are important for KCET, unless you are also preparing from some other exam. Okay, if you are solely focused on KCET, you have to understand which are the topics. So for MTG, if you can go, if you open the chapter, at the beginning of the chapter they mention which are the topics from where the questions came in the past. So that is one good thing about MTG book. Okay, so you can practice from that, but as I mentioned, not all questions are up to the mark of KCET. Either they are very easy or they are slightly difficult. So 50% question you can still practice from there. Okay, 50% question you have to unfortunately there are no very good books of KCET in the market. Okay, so that is one very bad drawbacks of any books that is available in the market. It is not about MTG, for all the books. Okay, I have seen Bosco as well. So Bosco also have not very standard books. Their quality decreased eventually, because initially when KCET used to be slightly difficult, when paper used to be slightly difficult, at that point of time Bosco was good. But now as KCET paper is not as difficult in the past, okay, 15 years back, 20 years back, KCET used to be slightly tricky. Some of the questions used to be slightly trickier. Now KCET questions are more or less easy. Okay, and that is why Bosco is not that good in my opinion. Okay, I don't think that Bosco, anyone purchase Bosco anymore. Okay, so now so what happens is that when you give a charge to a conductor, only suppose the positive ion is left, you might say that ion should stay inside the metal, inside the conductor, but actually it will not. It will somehow transfer the electrons. So it will, what it will do, it will take electrons from the neutral atom at the top. So it will take the electron and it will become 0 again, but the outermost surface will become positively charged. So whatever charge you give, the charge will somehow find on the surface of the conductor. It will not reside inside the conductor. So it is like a ball. If you have a plastic ball, you put it inside the water and you release it, the ball should come float on the surface, right? So this is the property of a conductor. No matter whatever charge you put inside the conductor, the charge will always float on the surface. So inside the conductor there is no possible charge. Okay, so electric field should always be 0. Okay, potential, electric potential is constant. Electric potential is constant. Okay, electric potential is constant. Electric field is 0. Okay, electric field is 0. Electric potential is constant. If it is charged, electric potential will be constant. Now one more important part, so whatever is the electric potential at the center, the same potential will be on the surface as well. So there was a question in the past that electric potential inside the center is 20 volt. What will be the electric potential at the surface? So remember that electric potential, whatever is inside the center, the same potential will be on the surface as well. Potential does not change throughout the volume of the conductor. So if it is a conductor means charges are always on the surface. Okay, for non-conductor it might change obviously, but for conductor remember that potential will be always constant from center till the surface. After that it will change. Okay, electric field is 0, potential is constant. Okay, Now obviously our Pariksha Veera batch, so we are going to have another session today in the afternoon, 6 p.m. You can join us to know more about this batch, where we will discuss some other things as well as our more detail about our Pariksha Veera batch. So please do join us there to know more about it. For now, Pariksha Veera batch class is starting from 6th of July. The price of the batch is 3499 only. Okay, and it is a inaugural offer, launch offer, price might change later on. So now let's move on to electrostatics. Electrostatics shielding. What is electrostatic shielding? Suppose you have a metal, full metal, okay, and inside the metal if you create a cavity means a hole, okay, you may have heard about the advertisement where they said cavity inside your teeth. So cavity means a hole, okay. If there is a hole inside the metal, okay, inside that hole also electric field will be zero. All the electric field will not go inside this conductor, so electric field will pass outside the conductor and outside the hole, and electric field will be zero, potential will be constant. That means it will remain unaffected from any electrical interference that is happening outside. So that is very, very important part to understand. That's why any sophisticated instruments, they are kept inside a metal box or in a room completely covered with metal sheet. Okay, for example, one such example is MRI machine. MRI machines are basically highly sensitive magnetic material, so they cover the room with a non-magnetic metal. Okay, so they cover the entire room in a non-magnetic metal, so that obviously they do not interfere with the magnetic field, but yes, any electric interference is pushed out by covering it in a completely metallic room. So there are multiple other devices as well, so they are kept in a metal box so that they do not get affected when any electrical interference is happening outside. Okay, so that is very, very important, especially the some sophisticated measuring devices, they are always kept inside metal boxes. Okay, so inside a cavity electric field is zero and potential is constant, right? That is called electrostatic shielding. Okay, basically it is shielding the device from any electrical interference. Okay, and there is one more example, is that if there is a thunderstorm happening in the atmosphere, if you are sitting inside a car, which is safe, staying inside the car or going outside? It is always safe to stay inside the car, because even if the thunderstorm hits you, because of the car is made up of metal, okay, you will still be insulated from the electrical interference. That is one important lesson. Okay, now we moved on to dielectric. So what is dielectric? So dielectrics are non-conducting substances. Basically dielectrics are insulators, okay, and so basically dielectrics behave slightly differently than that of conductors. Give me a moment, please. So basically dielectrics are insulators, and why they are called insulators? Obviously they do not have any free charge carriers. So for metals they have a lot of charge carriers. Conductors, insulators, they do not have insulators, they do not have a lot of free charge carriers. Either they are almost zero or negligible. Okay, and so basically dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. So charge carrier means electrons, free electrons, okay, or ions. So neither they have ions nor they have free electrons. Everything is sitting inside, tightly inside the molecule, okay, and molecule basically is keeping everything together, okay. So positive, negative, everything is sitting inside the molecule itself. Obviously they have charge, positive, negative, but they are not free. They are not free, they are not allowed to move freely. So basically it's a very strict classroom where teacher is making sure everyone is sitting inside in their particular position. They are not allowed to move, so they are basically strict free, okay. It turns out that in the external field induces a dipole moment by stretching or reorienting the molecules of the dielectric. The collective effect of all the molecular dipole moments is net charges on the surface of the dielectric, which produce a field that opposes the external field. So in case of dielectric also, when you apply an external electric field, okay, this is happening in metals. In case of metals, internal and external electric fields are same, so they cancel each other. In case of, so this is the conductor. So if you remember, this is the conductor where you apply some external electric field, and in the presence of external electric field, what happens? So this is the external electric field. There is an internal electric field developed. So external and internal, they cancel each other, right? For metals, they cancel each other. So net electric field inside is 0. But for dielectric, something important happens is that when you apply external electric field, okay, there is also an internal electric field. By the same way, electrons move away in one direction, the molecular positive charge moves away in another direction, so they form dipoles. So we will discuss about that in a detail in a while. So that is called dipole. Obviously dipole means one positive and negative charge. So positive and negative charge combined together, they are called dipoles. And these dipoles, what they do, they align, basically their only job is to align according to the electric field. So negative charges all move in this direction, positive charges all move in this direction. It does not happen by motion of the charge, it only happens by alignment of the charge. That is very, very important. Charges do not move, they only align themselves, and because of the central portion, all the positive, negative, they cancel each other. Okay, we will see that in the polarization part. Now what happens, this all negative charges accumulated over here, all positive charges accumulated over here, so they basically give rise to a internal electric field. So there is an internal electric field which is from positive to negative. So there is an internal electric field which points from positive to negative. Now this internal electric field does not match with the external electric field. They are smaller. Internal electric field is smaller compared to the external electric field. So basically dielectric does not cancel the external electric field, but it only reduces it. So this is very, very important, okay. So for conductor, entire electric field is 0. For dielectric, the electric field is only reduced. It cannot be cancelled, it only reduced. So dielectric basically reduce the external electric field. The opposing field so induced, it does not exactly cancel the external field, it only reduces it. The extent of the effect depends on the nature of the dielectric, right? So basically it varies from dielectric to dielectric. If it is a good dielectric, it can reduce significantly. If it is a bad dielectric, it can reduce slightly. Okay, obviously it depends on the nature. Okay, and that's why the term called dielectric constant. Okay, now we are discussing about the dielectric constant or relative permittivity. Okay, so what is the dielectric constant basic definition? So basic definition of dielectric is the permittivity of the medium, so how much electric field it allows through it, and permittivity of the free space. Okay, so permittivity of the medium divided by permittivity of the free space, that is the dielectric constant of a particular medium. It is denoted by epsilon r or capital K. Okay, relative permittivity or dielectric constant, both are same thing. Relative permittivity and dielectric constant, they are same thing. So if you see in a question that relative permittivity is mentioned, don't be afraid, relative permittivity is same as dielectric constant. Okay, and one more important part is that dielectric constant can be defined in terms of electric field as well. Okay, dielectric constant is basically the external electric field that you have applied divided by the net electric field developed inside the conductor or the material inside the material. So that is the ratio of the external electric field to the net electric field inside the material. So that is also a definition of dielectric constant in terms of electric field. So that is very, very important to remember. Okay. Now, so if you see that there is a MCQ question, dielectric constant of a metal or a conductor, or relative permittivity of a metal or a conductor. This is a board level question, very popular, especially for your midterm and beyond. Okay. So what is the dielectric constant of a metal? So dielectric constant of a metal is basically, so if you see that if you apply a net electric field, the net electric field inside the metal will be 0. So that means dielectric constant will be infinity. For a metal, the dielectric constant is infinity. Okay, dielectric constant for a metal is infinity. Okay, so inside the conductor, dielectric electric field is 0. That's why the dielectric constant is infinite. So that is very, very important to remember. Now let's see one question. Two charged spheres separated at a distance small d exert a force capital F on each other. If they are immersed in a liquid of dielectric constant K, then what is this force? So this is very interesting, important question. Okay, common question, not very difficult. So basically what happens is that we have two charged spheres, say this one is as Q1, this one is Q2, and inside there is no material is there, only air is there. So air's dielectric permittivity is epsilon naught. So what is the force between them? According to Coulomb's law, F is equal to 1 by 4 pi epsilon naught. Obviously do not write K over here. F is equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square. Okay, R is the distance between the spheres, right? So this is the first force. Now if you take this entire arrangement and put it inside a dielectric medium without changing their distances, okay, so dielectric medium of constant capital K, now what will happen? Will this force change? So first of all, so this force is dependent on the permittivity of the medium. So normally we write 1 by 4 pi epsilon naught because we assume that the space is free space or it is air, right? But if the same system is put into a dielectric medium or on a medium where it is not free space or air, then you have to modify this force formula. How to modify? You have to modify it by using 1 by 4 pi only epsilon Q1 Q2 by R square. So this part remains same. This part remains same because this is coming from Coulomb's law. Coulomb only says that it is proportional to Q1 Q2 and inversely proportional to 1 upon R square. He did not give the proportionality constant. Proportionality constant people came up with after solving the equation and after solving this. Basically this proportionality constant comes from Gauss's law. Okay. So after doing the Gauss's law, they realized the proportionality constant is 1 by 4 pi epsilon naught. Okay, in the past when CGS unit of charge was there, they tried to make this proportionality constant equals to 1 as well. Okay, but in SI unit, when they realized CGS unit will not work, they have to define a new unit. So there they found out that this unit cannot be 1, it will be 1 by 4 pi epsilon naught. So that's how everything progressed. So this is history of science. We are not discussing history. But you have to, only thing that you have to change is this epsilon naught should become epsilon. So epsilon is the permittivity of that medium. Now what is permittivity? We know that dielectric constant is basically permittivity divided by free space permittivity. Okay, so from here we can write epsilon equals to dielectric medium into epsilon naught. So basically you have to replace this equation by writing 1 by 4 pi epsilon naught into K. Okay, and everything else will remain same. Okay, so that means the force will be F by K. So force will be F by K. Okay, so correct answer is F by K. Easy question. Now let's move on to dielectrics can be classified into two categories, polar and non-polar. Okay, so far we have discussed conductors. Conductors are basically only one single category, but for dielectrics which is very interesting. They can be categorized into two special categories. One is called polar and another one is non-polar. Okay, so what is non-polar? In a non-polar molecule, the centers of positive and negative charges coincide. So based on this line, there was a question in your board exam once. Okay, in a non-polar molecule, the centers of positive and negative charges coincide. The molecule then has no permanent or intrinsic dipole moment. Examples of non-polar molecules are oxygen, hydrogen, molecules in which because of the symmetry have no dipole moment. So basically a non-polar molecule can be drawn like this: a positively charged center and a negatively charged electron. So they basically are coinciding on the same position. Okay, basically if you draw it like this, positive center and electrons, they are basically located at the same position. So center of the charge is basically at the same point. So for example, suppose you consider a atom. So this is the center, positively charged center. Electrons are orbiting around this. You might say, sir, that there is already a difference between them. There is already a distance or gap between them. How can they coincide? So that is one question. When I was a student, I asked my teacher, sir, how can they coincide? Basically, if you consider the position of the electron, electron is not static, it is constantly rotating. So if you want to take the average of the electron's motion, it will pass through this center. That means the orbit is perfectly circle, and that's why the average position of the electron passing through this is the center. So that means the positive center and the negative electron, their effective positions are same. Okay, so effectively positively charged nucleus and negatively charged electron, they are falling over one another. That's why they do not have any polarity, so they do not show any dipole moment. So net dipole moment in the molecule level, very important, net dipole moment in the molecular level is 0, and that's why they are called non-polar. Okay, polar we have studied somewhat in chemistry as well, but non-polar maybe not so much. So non-polar means positive and negative charges, the center of the positive charge, center of the negative charge, they coincide over another. So they do not have any net dipole moment. Molecular level, okay, molecular level, they do not have any net dipole moment. That's why they are called non-polar dielectrics. Okay. A polar molecule is one in which the centers of positive and negative charges are separated even when there is no external field. Very important. Okay, such molecules have a permanent dipole moment. An ionic molecule such as HCl or a molecule of water H2O are examples of polar molecules. Note, in a polar crystal, the net dipole moment is 0. This is because the molecular dipoles are randomly arranged. I will come about this later on, but if you have studied the chapter solution, there you have learned that water is a universal solvent, because one of the property of water was water is basically a polar molecule, so that it can attract polar as well as it can attract non-polar as well. So basically that's why water is one of the best solvent that is available to us, right? So so maybe you at that point of time you are not aware what is polarity. So polarity means they have a net dipole moment. I take the example of water only. So water has oxygen atom, okay, and it has 2 hydrogen atom. Okay, angle between them is slightly less than 120 degree or slightly more than 120 degree, if you don't remember it, but yes, they are not exactly 120 degree, so they are arranged like this. Okay, now what happens is that so hydrogen is giving 1 electron to the bond, oxygen is giving 1 electron to the bond. Similarly here also hydrogen is giving 1 electron, oxygen is giving another electron. So basically it's forming a single bond structure, right? Now what happens, after giving the electron, oxygen is saying, see, I am a big brother, I have more electron affinity, so why not, even though after I am giving you the electron, why not you return me the electron back? So what it does, it takes the control of these electrons and it moves closer to the oxygen atom. Similarly, both bonds, what happens, the electron actually moves closer to the oxygen atom. Okay, so even after giving the electron, they form the bond. After forming the bond, they are basically saying, okay, we have successfully performed the bond, now let me keep the electrons for myself. Okay, so basically now what is happening is that even though this electron was given by hydrogen, now hydrogen is almost have no electrons, so basically it becomes slightly positive. Okay, this also becomes slightly positive, whereas the oxygen becomes slightly negative, 2 delta minus. Okay, so now we know that there is a dipole moment which forms from negative to positive. So there is a dipole moment formed from positive to negative, and there is a net dipole moment which is downward. In chemistry, maybe you are using the opposite sign. Okay, in physics we use the dipole moment from negative to positive. We already know that, right? So dipole moment is developed. So net dipole moment. So this is the net dipole moment, and because of that water is a polar molecule. Okay, now when all this, now when we are drawing this, we cannot draw this structure every time. So for a polar molecule we use the symbol like this, negative positive. So this is the symbol of a polar dielectric. So this is the symbol of a polar dielectric. Now when multiple water molecules are present, each of them have this kind of structure, one positive center, one negative center. So their centers are not aligned, they are slightly misaligned. Okay, and because of that they have a permanent dipole moment. Right, now what happens is that inside a polar molecule, the positive negative, even though they have positive negative, but they are randomly arranged. Okay, and basically if you just consider a 3 molecule system, okay, so basically they cancel each other. So the net dipole moment, they are arranged such a way that the net dipole moment in static situation is still 0, but this is crystal level. This is at the level of crystal. Molecule level, they have a permanent dipole moment. Crystal level, their net dipole moment is still 0. So that is a major difference between polar and non-polar. So polar, okay, they have molecular dipole moment, they have 0 dipole moment in the crystal level or a bulk level, okay, where multiple molecules are present. In case of non-polar, even a single molecule do not have any dipole moment. Okay, crystal level obviously it will be 0, but molecular level also it is 0. But for polar, they have a dipole moment in the molecular level, but in the bulk material they still do not have any net dipole moment. For example, if you take one single water molecule, you will find the dipole moment, but if you take a glass of water, okay, the net dipole moment will be 0. So that is the difference. So basically it is the picture in the presence of external electric field, how polar and non-polar molecules behave. So if you consider the polar ones, non-polar ones, so this is the non-polar, right, this is non-polar. Okay, what happens to the non-polar atoms? So non-polar basically have positively charged center and negatively charged electrons, and their centers are basically coinciding, so that means they have 0 dipole moment. So here there is no electric field, so they are all arranged like this. Now when you apply some electric field, okay, what happens is that the positively charged center, that moves in the direction of electric field, okay, and the negatively charged electron, they move opposite direction of the electric field, right? So when you apply some external electric field, the positive charge move in the direction, negative charge move in the opposite direction. So basically you get an internal electric field, developed in the opposite direction, and that's why the overall electric field gets reduced. Same with non-polar molecules. So non-polar molecules by default they have some dipole moment, so they have dipole moment, but they are randomly arranged, so net electric field is still 0. But when you apply some external electric field, what happens? The electrons or the negative center move in the opposite direction of the electric field, positive centers move in the direction of electric field. Now they have a net electric field. Again, not all the molecules arrange, but some of them arrange. So internal electric field is developed here. Okay, this is external, and there is a internal electric field. Okay, so electric field inside a polar or non-polar, they behave almost similarly in the presence of external electric field. In the absence of external electric field, their behaviors are completely different. Hi Murtaz, Mutturaj. Hi. If you have any questions, feel free to ask me in the chat. I will try to answer. Now, which of the following correctly describes the behavior of polar and non-polar dielectrics in an external electric field? So this is a question. Both polar and non-polar dielectrics have permanent dipole moments, but only non-polar dielectrics align in an external electric field. So obviously this statement is incorrect, because only polar have permanent dipole moment, but non-polar does not have a permanent dipole moment. So that means first statement is incorrect. Polar dielectrics align their dipole moments with the external electric field, while in the case of non-polar dielectrics, the dipole moment is induced in response to the field. Okay, so this is basically correct. If you see that polar already have a dipole moment, they align their motion, their arrangement in the external electric field. Non-polar, they do not have any dipole moment. They are basically whatever dipole moment is produced inside them in the presence of electric field can be considered as a induced electric field. So that is induction of dipole moment. So in the presence of external electric field, a dipole moment is induced in the non-polar dielectric. So this is the correct statement. Let's check the other statement as well. So whenever you are solving an MCQ, maybe it's KCET level or board level, always remember, check all the options, do not ignore any other options. Okay, non-polar dielectrics align their permanent dipole moment. So non-polar dielectrics align their permanent dipole moment. They cannot align because non-polar dielectrics do not have any permanent dipole moment. So this statement is incorrect. Polar and non-polar dielectrics behave identically in the presence of an electric field, showing no difference in polarization. Obviously polar and non-polar, they do not behave exactly same. Okay, even though they do reduce the external electric field, but their behavior is different. For example, polar, they align their electric field. Non-polar, they separate, their centers separate, so and dipole moment is induced inside them. So this statement is also not correct. Even though it is very, very close, it is not perfectly correct. That means correct statement is option B. Right? Now let's move on. So now when you apply an external electric field, the dipoles are now aligned. Okay, either created or they are aligned. So that process is called polarization. So basically, whether a polar or non-polar, a dielectric develops a net dipole moment in the presence of an external electric field. The dipole moment per unit volume is called polarization and denoted by capital P. For linear isotropic dielectric, P is given by P is equal to epsilon naught chi E vector. So when you apply some external electric field, in the presence of external electric field, the dipole align their internal dipoles for polarized molecules, and for non-polarized, they basically induced a dipole moment, and then again they align their motion. So that's why this is called polarization. So by default, in a crystal level, be it polar or non-polar, both they do not have any crystal level dipole moment. Net dipole moment still 0. But when you apply an external electric field, the net dipole moment no longer remains 0 for both cases. So that net dipole moment means in the presence of electric field. So net dipole moment per unit volume is called the polarization. So whenever polarization happens, you can calculate that the net polarization is denoted by this formula. So this formula based question I think came once, okay, where chi is called constant characteristics of the dielectric and is known as the electric susceptibility for the dielectric medium. So this is the electric susceptibility for the dielectric medium. Okay, so this is the electric susceptibility. Sometimes they might ask what is the electric susceptibility. Remember, electric susceptibility is basically polarization divided by epsilon naught E. Okay, this is the electric susceptibility. Okay, the polarized dielectric is equivalent to two charged surfaces with induced surface charge densities sigma p and minus sigma p. So suppose you have applied an external electric field. So this is the dielectric medium. Now in the presence of external electric field, positive and negative charges, they separated each other, and you can consider this entire area is like a positively charged, this entire area is positively charged, this entire area is negatively charged. So basically you can say that this having a surface charge density sigma p, this having a negative surface charge minus sigma p. As I mentioned, charges do not move, they only realign. So central position, all the positive negative, they cancel each other. In the central zone, if you see that positive negative, positive negative, positive negative, so they cancel each other. Central zone has no net dipole, no net electric field. So net electric field is between this surface and this surface. Okay, and obviously the net electric field inside the conductor will be from positive, from positive to negative. Okay, electric field will be from positive to negative. Okay, so this is the induced electric field. Okay. So the field produced by these surface charges opposes the external electric field. The total field in the dielectric is thereby reduced from the case where no dielectric is present, and we should note that the surface charge densities plus minus sigma p arises from the bound charge and not from the free charge. So these charges are bound charges, they are not free charges. So you cannot compare it with the free charge motion where positive and negative are opposite sides. So these are called bound charges. Bound charge means they are not allowed to move. They are not allowed to move. They are basically staying inside the crystal itself. That's why it is called bound charge. And free charge means when electrons can move from a metal atom to another outside, that is called free charge. It is possible for metals. For dielectric medium, free charge is not there, only bound charge is there. Okay, and this is called bound charge density. Okay, now so basically this is the end of this lecture. Now let's give me some practice question for you. So this is the first practice question. The dimension of electric polarization is given by. Try to figure out what is the dimension of electric polarization. Very interesting. Okay, we have purposefully not discussed. Okay, so dimension of electric polarization and dimension of electric susceptibility. Try to find them out. Okay, it will be interesting. So dimension of polarization and dimension of electric susceptibility, both are important. Try to find them and mention that in the comment what will be the dimension of these two quantities. Next question. Polarization of dielectric medium depends on only on external electric field, only on the susceptibility of the material, both A and B, none of the above. So on which the polarization depends. Again, remember the formula. If you remember the formula, you can answer this question easily. What was the formula? Polarization is given by epsilon naught electric susceptibility into electric field. So now you answer the question. Easy question. If you know this formula, you can answer this question. Okay. This is the end of this lecture, and before I go, I just want to remind you all that our Pariksha Veera batch is going to start from 6th of July. I know many of you have purchased it and still waiting when the batch will start, but if you trust me that many students were given a choice if they want to get a refund, but they said that we don't want a refund, we want to stay with the batch. So batch final date is 6th of July. It will start from 6th of July. Okay, the classes will start from 6th of July. I think the color is not visible. So classes will start from 6th of July. Okay, Monday. So don't be late. Join the batch in time. Classes will start and we will start every day there will be two classes, right? And you will get 500 plus hours of cassette live session by top teachers. It is actually 110 plus hours per subject. Okay, instant 24/7 doubt solving class. You will also get 20 plus mock test per subject, okay, with detailed analysis, etc. So everything will be provided in this batch, and the batch price is only 3499 only. Okay, so not high, not purposefully it is kept at a low price so that everyone can join and start their cassette journey for their top 1000 rank, right? So yes, this is the end of today's session. The PDF will be available in our WhatsApp channel, so don't forget to join the WhatsApp channel if you have not yet joined there, and obviously click on the link in the description section to purchase this batch, or obviously go into the description section for this lecture note if you really want to download it. And obviously I'll be back with the remaining part 3 in next Monday's class, so don't go anywhere. Subscribe the channel if you have not yet. Till then, bye.